Good day, everyone. Thank you for joining us today. My name is Zach Freitas, and I'm pleased to be joined by my esteemed colleague, Brianne Bell. Our discussion today will focus on a new methodology for identifying fraudulent job postings through the utilization of enhanced feature engineering techniques. We would like to present our agenda for today's presentation. To begin, we will provide a detailed overview of our problem statement. This will be followed by an in-depth analysis of our data extraction, transformation, and loading process, as well as our exploratory data analysis techniques. Subsequently, we will delve into our modeling process, highlighting its key components and specifications. We will then present our findings and discuss the results of our models, followed by a comprehensive review of our conclusions. Finally, we will offer suggestions for future refinements and next steps. Fraudulent job postings have become a critical concern, leading to a loss of trust, time, and future resources for both job seekers and job posters. In 2020, these employment scams have resulted in approximately $59 million in losses for victims. To address this problem, we propose utilizing natural language processing features and machine learning models to accurately identify and eliminate fake job postings. By doing so, we can reduce losses for victims, enhance company credibility, safeguard applicants' personal information and finances, and reduce the time spent on applying for fake jobs. The incorporation of NLP features into machine learning models can serve as an effective solution in combating fraudulent job postings. By employing these techniques, we anticipate achieving a notable improvement in the F1 score performance, surpassing the established baseline threshold of 46.2%. Job scams are a reprehensible strategy employed by fraudsters who utilize false online job postings to extract personal and professional information from job seekers under false pretenses, with no genuine intention of offering employment. These scams often result in significant financial losses, with more than $59 million reported as lost by more than 16,000 victims in the US in 2020 alone. A recent UK study has revealed that online job advertisements pose a significant risk, with losses exceeding 500,000 reported by nearly 700,000 job seekers. Disturbingly, students and recent graduates are frequent targets due to their eagerness to secure employment. Despite efforts to prevent cybercrime, scammers who perpetrate online recruitment fraud, or ORF, have continued to evolve their tactics, making it difficult to detect and combat these scams. ORF is a rapidly expanding field driven by the growth of online job boards and postings. To counter this, researchers have turned to machine learning, using text-based or categorical data, or a combination of both, to develop models that can differentiate between genuine and fake job postings. Among the simpler methods tested, random forest classifiers have demonstrated the highest effectiveness. Our study aims to improve upon these existing methods by implementing a variety of data pre-processing and modeling techniques associated with natural language processing. At this point, I'd like to hand over the presentation to my colleague, Brianne, who will proceed to discuss ETL and EDA.
Thanks, Zach, for the background and issues regarding fake job posts. I'm now going to go into some of the ETL, EDA, and applicable data wrangling that we performed. The data is from an open source Kaggle dataset and contains 17,880 rows and 18 columns. One column is a job ID or row ID, meaning each row was a new posting for a job, whether it was the job's first appearance or one of many. This column was removed as it was not needed for modeling. After removing the job ID column, we checked for duplicate rows and removed them. In total, we dropped 281 entries as we didn't want to overemphasize items from the duplicates by having them in the dataset more than the others. The columns in the dataset consisted of categorical, binary, and text-based features. When looking at the missing features, we found that there was a spread of missing data. However, since most of the data was categorical or would be addressed with text manipulations, we chose to keep the missing data. It is interesting to point out that most of the missing data was for salary range and department. The target column, where it was classed as either a fake post as a 1 or a real post as 0, there is a severe imbalance where only 95% are real jobs and only 5% are fake. In terms of EDA, we will first look at the numerical, or more accurately, binary features. We looked at the Pearson correlation between the features themselves and with the target feature. None of these have a strong correlation value between themselves or the target. However, company logo and screening questions have a moderate correlation between themselves, while only company logo has a moderate negative correlation with the target, meaning not having a company logo is generally slightly related to the post being fake. While we did several plots to observe trends in the categorical and text features, these all had very high cardinality. This high cardinality means that there are a lot of unique entries, meaning that drawing meaningful conclusions from the EDA alone was very difficult. We did some text manipulations to make EDA possible with the text-based features. The text-based features included title, company profile, description, requirements, and benefits, which were all combined into a new column called all text. The text was then put in lowercase, with stop words and punctuation being removed, then the contents were tokenized. We then created word clouds for the description and company profile variables to highlight the different keywords in each, with the most common words being in larger font. Job description focused on words like team, work, and business, while the company profile is similar with emphasis on team, work, and services, indicating that the job description is likely reflective of the company profile or mission statement. To prepare for modeling, we removed all the text and tokenized text data except for the all text tokens variable. Second, we used TF, IDF to create feature embeddings of the text data, which increase the predictors from just the one column of text data to over 4,200 columns. Third, we take the categorical features and use one hot encoding to create dummy variables, which again increases the number of predictors, this time going from 8 to over 5,500. Fourth, we've combined the different data manipulations with the binary features, which included the target variable, to get a final data set of 9,730 columns and 17,599 entries. At this time, we also made a smaller data set that excluded the text-based features. These two data sets were then split into 80% training and 20% testing, while keeping the same 95% real and 5% fake proportions. With the knowledge that balanced training sets improve model performance, we decided to rebalance both of the training sets. To achieve this rebalancing, the training data was processed with SMOTE, or Synthetic Minority Oversampling Technique. SMOTE consists of synthesizing elements for the minority class based on those that already exist. It works by randomly picking a point from the minority class and computing the k nearest neighbors for this point. The synthetic points are then added between the chosen point and its neighbors. This technique gave us a balanced training set of 50% real and 50% fake posts in the target feature. I am now going to hand it over to Zach to cover the modeling methods we used.
Thank you, Brianne. Now let's delve into the modeling segment of our project. As previously discussed by Brianne in the ETL segment of our presentation, we partitioned our dataset into two distinct training sets. The first training set comprises only of categorical and binary features, while the second training set contains the aforementioned features and TF-IDF feature embeddings from our free-form text data. For the former, we shall employ two machine learning models, naive Bayes and logistic regression, whereas for the latter, we shall employ four machine learning models, naive Bayes, logistic regression, random forest, and gradient boosting machine. The rationale behind selecting these models is their varying approaches and methodologies for effectively addressing our classification problem. Initially, we shall discuss the training of our baseline models that exclude the text-based features. Our initial model without textual features, multinomial naive Bayes, is a popular Bayesian learning approach widely used in natural language processing for classifying documents based on statistical analysis of their contents. We chose it as our baseline model due to its simplicity and prevalent use in this domain. Although the training phase produced high scores for all evaluation measures, our validation set showed a different story. While accuracy scored a promising 91%, the F1 score was a poor 46%. Given the imbalanced classes in our data set, we opted to utilize F1 score as our primary evaluation metric, as it prioritizes false positives and false negatives, which are more critical in our case. The low F1 score suggests that the model is underfitting and may require further hyperparameter optimization or additional feature introduction or data. During the study, we assessed only one hyperparameter, alpha. Our second model with textual features, logistic regression, is a linear classification algorithm suitable for binary classification problems. Despite the similarity and the linearity of both naive Bayes and logistic regression, naive Bayes determines the data generation process based on the outcomes, while logistic regression predicts probabilities using a direct functional form. The training phase of this model resulted in high scores for all evaluation measures, whereas the validation set presented a different outcome. The F1 score for the validation set was poor, 44%. During the study, we assessed only one hyperparameter, namely C, which is the inverse of the regularization strength for our L2 model. Exploring alternative solvers or penalty approaches may present an opportunity for further improvement. Let us now proceed to examine the outcomes achieved after training the models with the incorporation of text-based features. Our initial model with text-based features, multinomial naive Bayes, demonstrated a substantial improvement in both the training and validation phases, indicating that the inclusion of text-based features has significantly enhanced the model's performance. Despite observing a remarkable improvement in the validation set, achieving an F1 score of 76% still fell below our expectations. Our second model, incorporating text-based features, logistic regression, similarly exhibited significant enhancements during both the training and validation phases. Although the training model appeared to be perfectly fitted, we must exercise caution regarding potential overfitting. Nevertheless, our validation set yielded an F1 score of 84%, which surpasses both the original score with the same model and our current baseline score, indicating that the addition of text-based features has positively impacted model performance. Our third model incorporating text-based features is the random forest algorithm. It is a popular machine learning technique that is widely used for both regression and classification tasks. This algorithm is based on the ensemble learning approach, which involves combining multiple decision trees to form a forest. Each decision tree is constructed using a randomly selected subset of training data and a randomly selected subset of features. The final prediction is then made by aggregating the outputs of all the decision trees in the forest. This method helps to reduce the risk of overfitting by smoothing out individual predictions and providing a more accurate overall result. Random forests are known for their robustness, scalability, and ability to handle various input data types. Logistic regression, on the other hand, performs better when the number of noise variables is less than or equal to the number of explanatory variables, whereas random forest has a higher true and false positive rate as the number of explanatory variables increases in a data set. In our study, the training phase of the random forest model resulted in slightly lower scores for the overall evaluation measures compared to the previous two models. However, it is noteworthy that the validation set maintained similar scores to the training set with an F1 score of 75%. During this study, we only assessed one hyperparameter, i.e. whether or not to bootstrap the model, and the best performing training model was obtained when the bootstrap parameter was set to false. Our fourth model with text-based features is the gradient boosting machine algorithm. which is a popular ensemble learning method for regression and classification tasks. The primary objective of GBM is to sequentially train multiple simple models, such as decision trees, on the errors of the preceding model to decrease the residual errors in their predictions. In contrast to random forest, GBM combines the predictions from all the models in a weighted fashion where the weights are determined by the performance of each model in the training data. Moreover, in GBM, each model is trained on the residuals of the previous model with the aim of minimizing the overall error of the model. A significant difference between GBM and random forest is the way the models are combined to make a prediction. In random forest, each decision tree is trained independently and the final prediction is made by taking a majority vote across all the trees in the forest. In contrast, GBM combines the predictions from all the individual models in a weighted manner. Another difference is the way that the models are constructed, where random forest uses a randomly selected subset of training data and features to train each decision tree, and GBM trains each model on the residuals of the previous model. Our study showed that training phase of the gradient boosting machine algorithm produced a near predictions. Similar to the logistic regression model, the validation set yielded an F-score of 79%, which was inferior to the results achieved by the logistic regression model. We evaluated only 2 hyperparameters for gradient boosting machine and believe that further exploration is warranted. At this juncture, I would like to transfer the presentation to my esteemed colleague, Brianne, who will provide insights into the results of our project.
Thanks, Zach, for conveying the models that we used. I am now going to go over the overall results and what that will mean for you and for future endeavors in finding fake job posts. Really interesting results. First, removing the text data resulted in models that had an F1 score of less than 50%. Second, the text-inclusive models all performed with F1 scores above 70%, with the logistic regression being the best at 84%. While we use the F1 score to determine the best model and parameters during model tuning, we also collected 4 other model performance metrics. They are accuracy, or the percentage of data points correctly predicted out of the total data points, the AUC, or the area under the ROC curve, where the true positive rate is plotted against the false positive rate. The higher the AUC value, the better the model did with classifying the target variable. Precision, or the percentage of data points correctly predicted as fraud out of the total instances that are predicted as fraud. Or recall, the percentage of data points predicted as fraud out of the total data points that are actual fraud. And the F1 measure, which is the harmonic mean of precision and recall. When comparing all of the models and datasets, the logistic regression, using the text-inclusive data, outperformed each model in every metric except for precision, which was best with the random forest model. The top 22 features of the text-inclusive logistic regression model, 21 of those features are from the text embeddings, while only the Department of Information Technology was the lone non-text feature. When we looked at the lowest important features, there was an even split of text and categorical features, with 3 of the 5 categorical features relating to location. This information further cements the need to include text-based data and possibly treating the location data differently. So what does this mean for you? The primary answer is that text embeddings work and improve your ability to spot fake job posts. Secondly, logistic regression works well at developing models that perform well at finding fake jobs while not being as computationally expensive as more complicated models. However, we do admit that there were limitations to our experimentation that could be addressed in future experiments for better performance. The first instance of improvement is to do a deeper dive into hyperparameter tuning to get even better models. The next area of potential improvement is to try different data manipulations with an emphasis on using country or state codes to limit the variety of locations. The third potential improvement is to just try other models, even the more complex ones. And our final bit of advice for after you Settle on a model is to get a fresh set of data from one or many job boards to test your model on to see how performance has changed, while the fraudsters have gotten sneakier since this data set was released. Thank you for your time and support. We hope to continue working with you and developing improvements.